Lewis structures and the shapes of molecules, and ions for that matter. The Lewis structure shows the arrangement of electrons around an atom or the atoms within a molecule or ion. The number of electrons that each atom provides can be seen from the periodic table. Oxygen, for example, has got 6 outer electrons, nitrogen 5, carbon 4, hydrogen 1 outer electron. So whenever we have atoms bonded together, then the number of outer electrons that there will be in total will be the sum of the outer electrons of each of the component atoms. Take for example carbon. Carbon is in group 4. It has 4 electrons. These 4 electrons can be represented as little x's like this, and the carbon atom itself isn't stable. It doesn't have a full outer shell. When it bonds to as many atoms as it needs to make a full outer shell of electrons. We can see that hydrogen, which has got 1 electron in the outer shell, could bond to carbon here using 1 electron from the hydrogen, 1 electron from the carbon, and that would make a bond with a shared pair of electrons. But clearly this could happen on all 4 sides. We could have 4 hydrogen atoms, each providing its own electron, to make a total of 8 electrons around the central atom. And this would give us our final Lewis structure around the molecule. And the question is, what shape is this? Well, the Lewis structure gives us the number of electron pairs or regions of negative charge. These will repel as far apart as possible, but we mustn't forget that it's a 3-dimensional shape, and a 3-dimensional shape will have a tetrahedral orientation. This will allow the atoms to, or better said, the electron pairs, to be as far apart as possible. I'm having difficulty picking up this electron pair. There we go, far apart as possible. I can't get hold of this hydrogen. There we go. Let's bring this back in, and you'll see here that the bond angle, the expected bond angle in methane, and we'll put up here methane. Let's run away. There we go. Put that back there. Methane has got a HCH bond angle equal to a tetrahedral, perfect tetrahedron bond angle, which is 109 degrees 28 minutes, about 109.5 degrees. Alright, so if we then look at this with a different molecule, let's clear the screen. Let's imagine we have, say, a water molecule. Well, oxygen, from our periodic table, remember, oxygen has got 6 electrons in the outer shell, and water, of course, is H2O. It's going to bond to 2 hydrogens. Now, once again, each hydrogen, and let's move it right over to the right hand side this time to give us more room. Each hydrogen is going to be bonded by a shared pair of electrons. If we do our accountancy, well, the 6 electrons from the oxygens add to the 2 electrons from the hydrogens. That makes 8 electrons altogether. But we've used 4 in bonding, which means that there's still 2 lone pairs on the oxygen. Now once again, we should easily be able to see here there's 1, 2, 3, 4 regions of negative charge. So once again, these regions of negative charge are going to arrange themselves in the form of a tetrahedron. But this time only 2 of the hydrogens are going to be in the the shape. So oxygen occupies the central atom position, and 1, 2 hydrogens, and of course we've got 2 lone pairs. Now what would happen under this in this situation, we would expect the bond angle here to be 109.28, the same as methane. But in fact what happens is that the water, it's jumped again, the water bond angle is going to be squeezed together by the effect of 2 lone pairs which repel the bonding pairs more than the bonding pairs repel each other. And so the result of that is that this HOH bond angle is equal to 104 degrees, 104.5 degrees. The rough rule of thumb is that we lose about 2.5 degrees per bonding pair, lone pair bonding pair repulsion. So even though when it's drawn out in 2 dimensions, the water molecule looks to be linear, when we consider it in 3 dimensions we can see quite clearly that the molecule is going to be tetrahedral electronically, and the molecular shape is bent.